All right, hello everybody. In this video we're going to talk about this concept of strain. Up to this point we've been talking about stress, which we said stress is a force distributed over an area like average normal stress. Strain is like the result of the stress. So if I were to apply a force over some kind of area, and I can see I already drew two little examples. The one on the left here is an example of an object that's under compression, of course. And the one on the right is under tension. So I think that we could probably already imagine, I already have it drawn out, what would happen to the overall shape. So if I'm in compression, my object's going to, in essence, shrink, or it's going to compress, right? So I have this delta S up here, which is the change in some kind of distance along my object, and my delta S would become smaller under compression, and of course the opposite would happen under tension, where it gets longer. So let's go ahead and define the equation for average normal strain. So for average normal strain, we're going to use the Greek letter epsilon, and we do want to say it's average. In the same way we said our stress was the average normal stress, this would be our average strain, meaning if we took the average across the cross section. And we're going to say it's equal to, using those little S values we had up there, our final length minus my initial length divided by my initial length. And if you look at the units, what we'd have is something like inches over inches, or millimeters over millimeters. You know, whatever unit you have on the top, you'd have on the bottom. So in essence, this thing is unitless or dimensionless. But we put them in there anyways. So what we'll usually do is we'll just write it as inches per inch or millimeters per millimeter. So the other type, and that's all axial, and I didn't create an example for this because it's pretty easy. It's one of the easier concepts, right? It's just if something stretched 1 inch and its original length was 6 inches, it would just be 1 over 6. Not too crazy. The other type of strain that we need to talk about is shear strain. So we've had this concept of shear stress before, and if I were to draw a cube on the ground, something like that, then a shear stress would be, we said it is along the surface or parallel to the surface. This would be my shear stress. If that's my shear stress, what I end up with is a deformation of this block, where I get something that kind of goes like that. The whole thing gets pulled over to the side slightly. And that change in shape is a result, or is what we're calling our shear strain. It results from the stress. The strain that we're actually measuring is this little angle right in here. And this little angle we're going to call gamma. Actually, let's put it inside here. Give myself a little bit more room, because what I'm concerned with in this case is how long or how tall. I'm going to use L because that's just the notation that I have in my equation. And then what kind of change in overall shapes my delta would be. Now, just looking from trig, I know that if I wanted to look at this gamma, that would be equal to the inverse tan of the opposite over the adjacent. But what we generally do is we use small angle approximation, because these are going to be very small. And so what that means is it's just actually equal to the delta over L. So you're just dividing how much it changes in one dimension over that length. However, you should note that this would be in radians if you were to do that type of small angle approximation. So for an equation, I can just write it out as you have it in one simple place. Our gamma is equal to our delta over L for our shear strain. So let's take a look at an example of that. All right, so here I have an example of a of a square. Looks like it's pretty square. Yep, 50 by 50. And then some kind of loading is applied to it, and I have these new dimensions designated by these little dotted lines with the blue, and we want to find the strain at A and at C. Now, if I were to look at A, I'm already given the angle. So I'm given that this angle is 91.5 degrees. So of course my gamma at A is equal to the 91.5 minus the 90, or its change of 1.5 degrees. Now the only issue there is when we talk about the shear strain, we do want it to be in radians. Maybe I should have put that in this equation. This should always be in radians. So we just have to convert degrees to radians. So I'm going to multiply this times pi over 180 for my conversion, giving me 0.0262 radians. Box that bad boy. For C, we're not given the angle, but we can calculate these the changes in the overall rise and run, right? So if I were to draw a line straight down here and making that a triangle, let me draw it down here because it's a little convoluted, and then we'll look at where these numbers are coming from. So what I have is I have a 53 millimeter height, and I have an 11 millimeter base. So where am I getting that? I can see that this is the 50 and the 3, adding those together, the 53, and I have the 8, but then I have to add that 3 in there to get at the 11. I'm trying to find the angle of this triangle, right? So this is my angle that I'm looking at. I could call that like theta, or I could just, actually this is what my strain would be looking like. So that's my strain at C, which is the same as theta, right? I mean, that's just a opposite interior angle type of thing. So theta is equal to gamma C, which is equal to the inverse tan of the 11 over the 53, and that gives me like 11.73 degrees. So convert to radians, what I end up with is gamma is equal to 11.73 times pi over 180, which gives me like 0.205 radians. All right, now you might be asking yourself, you said, hey man, 2 minutes ago you were saying that we can use a small angle approximation and we don't have to put in the tangent, and I could have just done 11 over 53. The issue with that is when you get these larger angles, small angle approximation kind of breaks down. So I would say if you're less than 5 degrees, you're definitely okay, maybe even less than 10. But let's take a look if I would have done that, if I would have said using small angle approximation. I don't know if you can abbreviate that, but I'm doing it anyways. It's a video. I would just end up with 11 over 53, and that gives me like 0.207 radians. So still very close. You could probably get away with using small angle approximation most times, but if you do have large shear strains, you could just throw in that tangent and then convert it to radians after the fact. So I hope that was helpful, and thanks for watching. I'll talk to you all soon.